So this lecture is on the gravitational force near Earth. So recall that gravity is an action at a distance force, or a non-contact force that pulls on objects. The reason why, or the reason how a non-contact force works is because it applies force over a certain field of influence, and a gravitational field has a stronger influence closer to the mass and a weaker influence farther away from the mass. So the gravitational field of Earth is a force field. It's a gravitational force field. The closer we are to Earth, the stronger that force is felt, and the farther you are from Earth, the weaker that force is felt. Sometimes we have a field being shown with a series of vectors, and in this case you see the length of the vector implies a greater magnitude. And the arrow head implies the location where the vector is acting. So the arrow heads that are touching the Earth have tails that are farther away from them, and the shorter tailed vectors are farther away from the Earth. So that's the idea of a force field, showing a force field using a vector notation. You also notice that because it is a purely attractive force, everything is pointing towards the center of the mass, which is at the center of the Earth. So we all have downward forces. So we can find the gravitational force at different points on Earth. When we find it, we call that the gravitational field strength. And it is equivalent to the force, the N, per unit kilogram. So gravitational field strength is measured in newtons per kilogram. And what's interesting is that the gravitational force on Earth is about 9.8 newtons per kilogram down. That should remind you of something from our previous unit. 9.8 meters per second squared is the acceleration near the Earth's surface due to gravity. And curiously enough, gravitational field strength, even though it's measured in newtons per kilogram, is equal to the acceleration due to gravity, because newtons per kilogram is equivalent to meters per second squared. So since the Earth is not a perfect sphere, the magnitude of the gravitational field strength at Earth's surface varies according to geographic location. At the North Pole, it's about 9.8322 newtons per kilogram. At the equator, it's about 9.7805 newtons per kilogram. That's because as the Earth spins, the locations that are spinning faster tend to have more mass, and that's why the gravitational field strength at the North Pole is greater, because you're actually closer to the core of the Earth at the North Pole than you are at the equator. Here it says to show that the units, newtons per kilogram and meters per second square, are equivalent. You can find something online to do that if you'd like. It's not that necessary to understand that. But this slide I'd like you to copy down. Gravitational field strength, it is the force per unit mass acting on an object in a gravitational field. It decreases as altitude increases. It varies according to the location, since Earth is not a perfect sphere. And it's about 9.8 newtons per kilogram on Earth. The gravitational field strength can be applied using the equation for Newton's second law of motion. So that's F equals ma, but in this case it's Fg equals mg, because a is our g, to determine the force of gravity acting on objects on the Earth's surface. So here's your force of gravity, Fg equals mg, where g is the gravitational field strength. Here's a question for you. It says the average mass of a basketball is 0.63 kilograms. What is the force of gravity acting on the ball? Well, if we put 0.63 times 9.8, and rounded it, you'd get 6.2 newtons, and it would be acting down because the gravitational force always acts down when we're on Earth. Another question, the force of gravity on a 250 kilogram spacecraft on the moon's surface is 480 newtons down. What is the gravitational field strength of the moon? So this one's a little bit more interesting, so we'll try this problem out. So we know the gravitational field strength on Earth, but when we're on the moon, things change a little bit because we know that the moon has about a sixth of the Earth's mass. So let's see what happens here when we try this question. So F equals mg. We have a mass of 250 kilograms. We have a force of 408. What is that g value going to be? 408 over 250. .408 divided by 250. 1.632, and we'll have to look at our significant digits in this question. We have 2 significant digits for 250. We have 3 significant digits for 408. So we round to 2 significant digits because that's the lower value. And we get 1.6 newtons per kilogram down. Now, another thing to consider here is 1.6 is about 1/6 of 9.8. So that's another way to see that the moon is 1/6 of the mass of the Earth. So the next part of this question says, what's the acceleration due to gravity? Well, it's equivalent. We just changed newtons per kilogram to meters per second squared. Here we have a 50 kilogram person standing on a bathroom scale inside an elevator. The scale is calibrated in newtons. It says draw an FBD to see what the person's mass would be, or sorry, what their weight would be when they are at rest. So we're going to do a series of questions like this. So for 5A, the person is at rest. So I will draw the free body diagram of the situation, and I will draw the or I will determine the mass of, or the force that the person experiences, their weight. So if a person's at rest, the Fn equals the Fg. Which is just mg in this case. And that's 50 times 9.8. It's 490 newtons for part A. Now, let's say that the elevator is moving at constant speed. So for an elevator to be moving at constant speed, we have to have a balanced force. That means that the Fg is equal to the Fn again, which means the mass reading stays the same, 490. What about if we're accelerating up at 2.2 meters per second squared? So we have an Fg, we have an Fn, but we have an acceleration up as well, which implies that there is an F net that is pointed upwards. So there is another force that's moving this person up. So there is an Fa causing motion, causing acceleration upwards. So now our F net is equal to FA. Sorry, our F net is equal to FA plus FN minus FG. And we have that equal to MA. In this case, we know our M and we know our A. We know our our FG as well. That's MG. So we need to just find out what is the reading on the scale. So it's going to be the equivalent to FA plus FN. So FA plus FN is equal to MA plus FG. And that would be, the person's mass is 50 times 9.8 plus the person's mass 50 times times 9.8. This is not 9.8, this is actually 2.2. That's the acceleration that they have, so 2.2. So I will do this calculation. So 50 times 2.2 plus 50 times 9.8 gets us to 600 newtons. So now we have a reading of 600 newtons on our scale. Let's do 5D, which will be a situation where I think we're moving down. In this case, we have our FG and our FN, of course, for our free body diagram. But there's also an FA. Because the acceleration is going down, that means we have to have an unbalanced F net that would be pointed down. So let's write down what our F net is, and because we're going down, we'll consider down as positive this time. FG plus FA minus FN is our F net. That's equal to our MA, and our A would be positive in that case because it's going down. So we need to find out what's the difference between this FA, FN. That's what our scale would say. So FA minus FN, that means we have to move this FG to the other side, so it's MA minus FG. And that works out to 50 times 3.0 minus 50 times 9.8. And this works out to negative 340. So why is it negative? Well, because we chose down as positive, then that's going to be negative. So ultimately, we know the solution is actually n up. So you might want to state that in that case. Just because we chose down as negative, that was that's why that came up as a negative solution.